Okay, just as a quick summary of what we saw a few seconds ago, I showed you that the total response, okay, was the sum of the zero state response and the zero input response. Okay, so this you could use this form of superposition to compute the response of these capacitive and inductive circuits, and just figure out the response to zero state and then figure out the response to zero input and sum them up. Okay, this way you can solve two simpler subcircuits to get the total response. Okay, now we are ready to dive into a major application of the state property of our circuits, state property of these capacitors and inductors and so on. Okay, and that is digital memory. Okay, so before we begin, let's first motivate why do we need memory? Although it's most of you are very familiar with memory in your PCs and other devices where you can store stuff, it's still worthwhile to take a closer look at why do we really need memory? Okay, and more importantly, to really try to understand why is combinational logic insufficient to do all the kinds of things we want to do. Okay, recall a few weeks ago we looked at combinational logic. And recall for combinational logic, the output at any given instant in time was a direct function of the input at that instant in time. Okay, so this is the input and this is the output. And the output at any given instant in time was a direct function of the inputs at that point in time. Okay, nothing else mattered. Okay, at time t, the output at time t was directly related to the inputs at time t, and that's it. Okay, that was combinational logic. Okay, so we'll start by looking at why is combinational logic insufficient for the kinds of things we want to do. Okay, so let's do a few examples. So first of all, consider adding a few numbers on your calculator. Suppose these numbers are 2 plus 9 plus 6 plus 5 plus 3 plus 8. So how do you do this? How do you go and do this on your calculator? Okay, how do you add a sequence of numbers, 2, 9, 6, and so on and so forth, on your calculator? The key there is that your calculator somehow remembers what you have done so far. Okay, you might also use the memory plus button of your calculator, or you might keep on accumulating the partial sum as you keep on adding additional numbers. But fundamentally, you are remembering your partial result. So let's say, for example, you start off with 2 plus 9. So at this point, your partial result is 11. Okay, then you add 6 to it and your partial result is 17, and so on and so forth. So the moment you add 5, your partial result was 17. This means that for the purpose of adding these numbers together, you could care less what the specific numbers were before this point in time. Okay, 17 completely summarized all the inputs you cared about until this point in time. Okay, and so 17 is your state. Okay, and you add 5 to that and so on and so forth. So memory is clearly important to remember partial results as you keep on doing things in sequence. That's one example for the need for memory. A second reason why you might need memory is to remember transient inputs. Okay, if let's say, for example, you're looking at some signal and you're trying to measure these signals, and these signals are transient. They sort of come and they go away. Okay, so oftentimes it's useful to capture the signal and store it so that you can process it later. Okay, so remembering transient inputs is a second example. And of course, the last one and the most important one probably is one that you don't need any explanation for, and that is just to store data. Okay, you can store music and videos and all kinds of stuff in memory, okay, and in your computer and so on, and that has to do with memory again. Okay, so with these examples to motivate memory, let's dive right into trying to build a memory cell. Okay, so I'm going to start by a very, very simple abstraction of a 1-bit memory element. Okay, I'm going to build you an abstract 1-bit memory element. So this abstract memory element might look like this. Okay, this is an abstraction. It's a 1-bit memory element. I'm going to call it M. It's a 1-bit element, and so it has a stored value, and that stored value appears at dout. Okay, so whatever value it has stored in it can be read on the dout wire. Okay, I can apply some input, and the input is called din. And then I need some kind of a store signal. Okay, the store signal will tell the memory cell, okay, replace the existing value with the new value from din. So I can draw you a little I can draw you a little diagram for how this might work. Okay, so how might something like this work? So the best analogy I can think of before I show you how this would work is to show you a little camera. So supposing I have a little camera. Let me try my best rendition of a camera. So here's my camera, and the camera has some film, and the camera has a shutter release button, and here's my shutter. So let's say I have some tree here, and the image appears on the film. So when I depress the shutter button, okay, a small opening forms, and the image of the tree impinges on the film. Okay, whether it's digital, some digital medium, or in the older cameras was real film. This begins to imprint itself on the film as long as the shutter is open. And after some time, the shutter closes. So there's think of it as a little pulse. So it's open for a short period of time, and then it closes. It was closed to begin with. It opens for a brief period of time, and then it closes again. So during that time, while it's open, the image of the tree will appear on the storage medium or the film. And when the shutter closes, that's it. Whatever was recorded until that point will stay there in that camera. So using this analogy, we can also build a very similar memory cell. Okay, so for my memory cell, here is what I have. So I can get a bunch of inputs. So let's say time is moving in that direction. So let's say I'm going to show you what happens at dn. Okay, so this is low and this is high. And this is store. This is low and this is high. And this is d out. Again, low and high. So let's say that d out starts at a low value. Okay, let us also say that store low and high. Let's also say the store starts off at a low value. Okay, and then let us also say that the input starts off at a low value. Okay, the world is very quiet and calm, nothing happening right now. Okay, so let's say I want to write a 1 into my memory cell. So right now it has a 0 in the memory cell. So to write a 1, I'm going to raise my input to a 1 for some period of time to a high, and then I'm going to make it the input go away. It doesn't matter. Okay, so the input is going to go high for some period of time. So to make the output go high, here is what I'm going to do. Okay, much like, so think of this d in going to a high, think of that as my image here. Okay, so that's my image here. I'm going to store that value. Okay, then I'm going to do the following. I'm going to create a little pulse here. Okay, I'm going to create a little store pulse. Think of that as my shutter release button. Okay, for a small period of time, store is going to go high, and then it's going to go away. So what I'd like to see happen is the following. Okay, so these are the interesting points here. Okay, notice that the pulse goes high at some point while the input is high, and my d out starts off being 0. And then what d out is going to do is that as the input value goes and gets written into the memory, my d out is going to follow whatever has been written in. Okay, so ideally, my d out for an ideal memory cell of this sort, d out might look like this. Okay, as soon as the store pulse goes high, the output d out will reflect whatever's at the input. Okay, so if it's an ideal memory cell, the output will reflect exactly what's at the input. And then when the store pulse goes away, whatever value was at the input gets stored on the memory cell, and that continues on being held inside the memory cell. So that value is held inside the memory cell. So fundamentally, when the pulse goes away, the last value that the memory cell saw before the pulse went down to 0 is what is eventually stored in the memory cell. Now, in a practical memory cell, it could happen that the output doesn't go to 1 instantaneously. Rather, it might go, meander up like this and rise up slowly, and then eventually settle down to its final value. And when the pulse goes away, that's what you see. Right? So the key here is that the memory cell M remembers the 1. Okay, it remembers the 1 at the input. Okay, so let me just write down some notes for you here so that you have it with you, and then you can refer to it later. Okay, so the input, when the input goes high, and the input is at a 1, for instance, when store goes high, the memory cell records that value on the inside and plays it out. Okay, so the input value at the instant that the pulse goes down, okay, so input value that was present the instant the pulse went away is what is finally recorded in the memory input. Okay, and this is like a camera that records its image when the shutter release button is depressed for a small instant in time. Okay, so the recorded value is visible at D out. So when store is high, the input value is being recorded into the memory cell, and that recorded value is visible at D out.